Algebra 2, Chapter 8, Section 4, Inverse Functions. An inverse function is a function which undoes or will undo the original function. For instance, if we have a function g of x, which means subtract 2 from the input, that's the inverse function of f of x, which means add 2 to the input. In general, a function g of x is the inverse of a function f of x if and only if the composition g of f of x is x for all x in the domain of f, and the composition f of g of x is x for all x in the domain of g. Now this is a lot of math language. Let's think about this with black boxes. So if we put, what we're saying is if we put a number into f, what we get out of that, if we put that then into this function g, and if we then get back out exactly what we put in, and if we do this for any number in the domain, we always get out the same number. So if I put in 2, I get out 2. If I put in 7, I get out 7. If I put in -3, I get out -3, assuming that all those numbers are in the domain of f. And it says, this is also true if I take any number in the domain, put it into g, and then put it into f, I again get back what I put in to start with. Okay, in other words, it looks like nothing happened to my number. That's why it's called an inverse. It undoes. And you can see if the rule to f were add 2 and the rule to g were subtract 2, it's easy to see that we would get back what we put in each time in either order. Often, or even really maybe they should say normally, maybe not normally in our book, but everywhere else, you will see the inverse of a function written as this, f to the -1 of x, as the inverse. And this comes from the fact, this idea of this notation comes from the fact that x to the -1 is 1 over x, using the rules of exponents. So this is communicating the idea that this function inverts the other function. This is not an exponent, it's just a superscript. This is just a mechanism of notating an inverse function. Okay, so don't get confused. This is not, if you ever see f to the -1, this is part of the name of the function. It all goes together. This is the name of the inverse function. It has nothing to do with making an algebraic statement about taking something to the -1st power, but it comes or is inspired by that idea. So to find the inverse of any function, we can do this actually pretty easily. And it seems really complicated at first, but I promise it's not that hard. I'll walk you through it here in the video. But to find the inverse of any function, give the output of that function a name and just solve for that name, solve for the output. So let's practice that. So we're going to find the inverse of each function. We'll start with a. Okay, so you could figure the inverse of this out without doing this technique, but this technique is so useful towards the end. We're going to do it every time we practice. Let's give the output of f a name. We're going to call it y. Y is f of x, okay? And we know that the output is equal to 6 minus 2x. Now we're just going to use the rules of algebra to solve this equation in terms of the input, which I believe is a mistake in my slide here. Okay, so this should say, give the output of the function a name and solve for the input. Okay, the function's rule will already be solved in terms of the output. So find the inverse of each function. Let's do this. So we have to solve for the input. So we're solving for the input, move 6 over. It means solve for x. In this case, divide by -2. And we've solved for the input. Now what? All we need to do is one little simple change of name here to get the inverse function. So if we just write the inverse function of f of x, let it be, and then we just take this as our rule, changing the placeholders, changing the names. So swap the name of the output for the name of the input. X minus 6, so swapping x for y over -2. That's the inverse of this original function, f of x. You might say to me, prove it. Well, we can prove it by doing the composition. If I compose these two functions, I better get back x. So the inverse rule was x minus 6. So let's first start with the inner. F of x is 6 minus 2x. So we have the inverse function of 6 minus 2x. Plugging this in when we see the x placeholder in the inverse function, we have 6 minus 2, x minus 6 over minus 2. So if we distribute the negative 2 in, these negative 2's will cancel. We'll have 6 plus x minus 6. 6 minus 6 is 0. We get x. Now we can do the same set of steps with the composition of f of the inverse of x, and we'll get the same answer. Part B, g of x is 2x plus 1. So let's find the inverse of g. We'll give the output a name. I'm just going to call it y again, and solve for the output. Sorry, I said it again. Solve for the input. It's already solved for that, but we've got to solve for x, the input. So divide by 2, subtract 1, and we're done. So the inverse of g is x over 2 minus 1. You might see basically a way of doing this without my technique by saying, okay, I just need to do the operations in the inverse order from normal. So normally we'd add 1 first and multiply by 2. So let's divide by 2 first and subtract 1, and we get the inverse. That works for simple functions, but we'll see how that gets harder to do as we go. So c, z of n, let's give that a name. We'll just call it z this time. So we'll solve for the input n. So add 2, it's 5n squared, divide by 5 is n squared. Take the square root. Now when we take the square root, there's really two possibilities, but this is a function. We can't have two possibilities. So that's why we just have to choose the positive one, and we'll have to restrict our range so that our inverse won't cover the whole domain of inputs. And that's okay, because we saw in the definition, if we go back, that we only have to be able to be inverting the things that are in the domain of both functions. Okay, so just restrict the domain to be positive or 0, so that we'll have n is, we should write plus or minus the square root. We'll do that right here, just to make the point that that's what we should do algebraically. But when we define the inverse function of z, we have to pick one, because the function has to have exactly one output. It cannot have two outputs. So the inverse function z, we'll just choose the positive square root, is the square root of n plus 2 over 5, changing the name of the input, of the output to the new placeholder that I chose, which was n. Okay, and this was, the domain for this was n is greater than or equal to 0. Right? No, not, sorry. The range is non-negative numbers. That's what we're talking about here, is the range. The domain of the original function was unrestricted, but the range of this function needs to match the domain of this one. We cannot put in something that's less than -2, right, into this function. So then we'll end up with a square root of a negative. So let's just show how to prove this is an inverse. So again, let's do the composition. Z of the inverse of n. So the inner function will be the inverse that we just created, square root of n plus 2 over 5. We'll plug that into the rule for z. So we'll have z, we'll have that this equals 5 times this whole input in where we see n. So 5 square root of n plus 2 over 5 squared minus 2. Square root of squared is going to give us back what we started with, 5 times n plus 2 over 5 minus 2 distributing in. The 5's cancel. N plus 2 minus 2 is just n. So we proved it's an inverse. So for part D, we'll give the output a name. We're just going to call it Q, since that's the name of the function, and solve for the input. Now here's where this technique is really important. It's a challenging one to invert otherwise. So to solve for Q, we need to multiply by the denominator. Sorry, to solve for X, we need to multiply by the denominator to get the X's to where we can get all the X's on one side and all of the not X's on the other side. So we'll have 9 times Q minus 7QX equals 3 minus 4X. Now getting the X's on one side, we have 9Q minus 3 is 7QX minus 4X. Factoring out the X, on the right hand side we get X times 7Q minus 4. Dividing by 7Q minus 4, we have a solution in terms of the input X. 9Q minus 3 over 7Q minus 4. So we can then write the inverse function by changing the Q's back into X's. Since I'm going to pick X for my placeholder again, 9X minus 3 over 7X minus 4. And we could plug that in, or we could do the composition and find that this is actually an inverse. But we're not going to do that today.